So today we're going to look at sets. A set is just a group of numbers or a collection of objects, and the things that are inside of the set are called elements. So a set is a group of items or objects, and elements are the things that are inside the set. Sometimes we call them members. We use these braces right here to have a set, or to denote that it's a set. So right here we have a set that contains the numbers 1, 2, 3, 4, and then this one is 2, 1, 3, 4, which those are the same thing. Order doesn't matter. These are exactly the same. This symbol right here, which you write by making a C and then putting a little line, this symbol means element of. So this is saying that 4 is an element of, we know it's a set because it has the braces, 1, 2, 3, 4, which is a true statement because right now we can see that 4 is inside of the set. This symbol means not an element of. So we draw the element symbol, we draw a line through it. So this means not an element of. So this says that 5 is not an element of the set 1, 2, 3, 4. This is us naming the set. So we're calling the set 1, 2, 3, 4 the name S, just like you all were given a name. N is what this set is called, and if you'll see that it has the dot, dot, dot. We use N to represent the natural numbers. Which you might have called counting numbers at some point in time. It's the numbers you learn to count with. So 1, 2, 3, 4, 5, 6, and it goes on forever. Then we have two kinds of sets. We can have a finite set, which means it has an ending with a fixed number of objects or elements. An infinite set has elements that go on forever. There's no counting how many elements are in the set, so it's never ending. Then we have the special notation, which is called set builder notation. And the first thing I want to, this little bar right here stands for such that. And so if we read this, the set builder says X such that X is a natural number between 2 and 7. So we want to write what that is. So it says it has to be a natural number between 2 and 7, not equal to 2 or equal to 7. So between 2 and 7 comes 3, 4, 5, and then 6. This is also known as a finite set because it has an ending point with a fixed number of elements. So now let's stay on that same thought process, and we're going to look at the example and name whether each set is finite or infinite, and then we're going to tell if 10 is an element of the given set. So on the first one, I have a starting point, I have an ending point. I'm going up by 1 every time, so I can tell the things that are in between here are 10, 11, 12, and then 13. That's a fixed number of things, so this is finite. And we can clearly see right here that 10 is an element. So 10 is an element. I'm going to name this set S. I'm going to write 10 is an element of S. The next one, so it says dot, dot, dot. I don't see a fixed ending, and this is going to keep going on. The bottom is getting 4 times as big, so I could do 1 over 256. And this would just keep going forever. So this is infinite. And nowhere in here am I going to ever see the number 10, because the biggest number I have right here is 1. And then I keep getting smaller and becoming more and more of a fraction. So 10, I'm going to name this one also. We're going to name this one S. 10 is not an element of S. The next one says x such that x is a fraction between 1 and 2. So if I want to write something that is in there, let's see, a fraction between 1 and 2. So 3 halves is in there. 8 sevenths. 9 eighths. 10 ninths. And I can go forever. I can name an infinite number of fractions, keep getting from 1 to 2, closer to 1, or closer to 2, but there are lots and lots of them. An infinite amount, in fact. So this is infinite. And 10 is not between 1 and 2, so if I name this set S, 10 is not an element of S. The next one says x such that x is a natural number between 9 and 10. So natural numbers are counting numbers, 9, 10, 11. So 9, what it says between. So the only number that is between them is 10. So first of all, this is finite. It has a fixed number of elements. And if I name this set S, 10 is an element of S. So let's try another example. It says use set builder notation and list all of the elements in each set. X such that x is a natural number less than 5. So let's see, less than 5. So natural numbers start at 1, 2, 3, 4. Have to be less than 5, so I cannot include 5. There's my set. Letter B says x such that x is a natural number greater than 7 but less than 14. So natural numbers after 7 so have to be bigger than 7. So after 7 comes 8, 9, 10, 11, 12, 13. And I'm going to stop because it says less than 14. Not equal to, but less than. So then I stop right there. So when we're discussing a set in a given situation or problem, we use the universal set to talk about all the elements that could ever be included, like the universe, and we use the letter U to represent that universal set. We also have some other special sets known as the null set and the empty set. The null set means there's nothing there, and we write that like this. Means there's nothing. We also can use the brackets, and then we don't put anything in them. So this, when there's nothing in between those brackets, means the empty set. So just a little warning. This is not the same as we don't want to write this right here, because what that said was I have a set that contains the null set. So that is not the empty set. That set itself has the null set inside of it. Every element of a set S, which is 1, 2, 3, 4, is a natural number. So S is what we call a subset of N, the natural numbers. And we write that by saying S is a subset of N, the natural numbers. Make sure you write the order matters. This is saying that the S goes into N. So to be a subset by definition, a set A is a subset of B if every element of A is also in B. So let's check. So here's A. 2 is in A and B. 5 is in A and B. 9 is in A and B. So if I were to write this, A is a subset of B. However, if you look at B, you can see right here, I have some elements that were not in A. So B is not a subset of A because B has some things that A does not have. So if we have some set A, these two statements are always true. A is always a subset of itself because A can always be contained within A. And the null set, the empty set, the thing with nothing, is also a subset of A. I'm sure you've seen what's called a Venn diagram before, but this picture is called a Venn diagram. And in my Venn diagram, I have the box on the outside. This box out here is the universe, all the space in the world. And then inside of that, I have set B. And inside of B, I have A. So if we look at this for a second, since A is inside of B, A is a subset of B. B is not inside of A, so we cannot. B has this red stuff out here. That is not inside of A, so B is not a subset of A. A and B, however, are also subsets of U, the universal set, because they live inside that yellow box. Two sets A and B are said to be equal if and only if A can be a subset of B and B is a subset of A, which means they are equivalent if they have the exact same elements. So let's take a further investigation of this. So I have some sets below. I have U, A, and B, C, and D. So the first question asks, is D a subset of B? So if we look at D, D has a 1, B has a 1. D has a 9, B has a 9. So this is true. D, the elements of D are also inside of B. However, the next statement says, is B a subset of D? And that's not true because I have 3 and 7 that don't show up down here. So this statement is false. Letter C says that C, the set C, is not a subset of A. So let's check. So I have 3, I have 3. I have 9, I have 9. 11 and 11. C is a subset. All of C's elements are in A. So this is also false. And then it says that U equals A. So remember, to be equal, they must contain all of the same elements. So let's look. So I have 1 and 1, 3 and 3, 5 and 5, 7 and 7, 9 and 9, 11 and 11, except this right here. 13 is not in A, so they are not equal because U has a 13 that A does not have. So there are certain things we have with sets. One of those is called a complement, which is written like this right here, and read as A prime. And so what that means is that if I am the complement, I'm all the other stuff. So if this right here is my A, right here, here's A, then everything outside of it is called A prime, or the complement of A, because it's stuff that is not inside of A. So for example, I have a set of students in a class who are 30 years old or older. So 30 and more. So here's my A over here is 30 plus. The universal set is all the students. So U over here is all. And then if I talk about A prime, if U is all of them and A is 30 and up, then A prime is 0 to 29. So let's use the idea of a complement and answer these questions. It says, given the below sets, determine the following. So it says A prime. So before we start, hang on. I need to make one little note. This right here is U. He's my universal set. So universal set means everything lives inside of me. So U is the big overarching set. It's like the outside of the box. Here's my U. And then inside of my U lives A and B, and they may or may not overlap. I don't know. They do overlap. They have a 3 in common. So just keep that in mind. So it says not A. So A prime means not A. So if I look at A, I have 1, 3, 5, 7. So I go back to my universal set, and I'm going to write down the things that are in U but not in A. So 1's there, but there's a 2 that's not over here in A. There's a 3, we're good, but a 4 and a 6. So this A prime is 2, 4, 6. B prime, same idea. What's in the universal set that's not in B? So I have a 1, a 2, I have a 3 and a 4, I need a 5 and a 7. The next one says the empty set prime, or not the empty set. So if I'm not the empty set, I'm everything, which means that I am U, the universal set. And not U, not the universal set, would mean that I am the empty set. Because everything's in U, so if it's not in U, then it doesn't exist. It's the empty, it's the nothingness. So we've talked about sets overlapping, so let's put some words to that. So if 2 sets overlap and contain some of the same objects, that is called an intersection. Or where do the groups, the sets overlap? Where do they cross? Where do they intersect? So look at the example. I have A and B, and the places that they overlap or have in common is 2. They both have a 4, a 5, and a 7. So to write the overlap, we write A, U, upside down U, B, which means A and B. So this intersection, we use the word, right? Intersection means and. Means what objects are in both A and B. If they have no items in common, they are called disjoint sets, which we can write as this. So let's try. Let's see where these two overlap. Well, it's not 9. They both have a 15. They both have a 25, not 20, and not 36. So the intersection of these two sets is 15, 25. On the next one, not a 1, 2, 3, 4, 2, 3, 4, not 5 and 6. So their intersection is 2, 3, and 4. The next one, they have no overlap. And if they have no overlap, they are called disjoint sets. And right here, we talked about that. So The intersection is the empty set. They have no intersection. Beyond the intersecting, where do they overlap? We have a thing called a union, which means or. So let's highlight that real quick. It means or, and we write it as a U, which is how I remember union. So it means this one or that one, or maybe in both, but it's just the two together. So this or this can be in either place. So we can write that as A union B, which means A or B, X such that X is an element of A or an element of B. So let's try. It says find the following. So this says, where does my first set union with my second set? You don't need to repeat elements. That is not needed by any means. So if I want to write that, oops. So I don't need to repeat. So 1, 2, 3, 4, 5, 9. Oops, forgot 8. Sorry, 5, 8, 9, 14. You don't have to write them in order. I just always have it, makes it easier. So I have 1, 2, 3, 4, 5, 8, the 1, 9, and 14. So there's your answer. Let's try again. So I have 1, 2, 3, 4, 5, 6, 7. There's my union. Okay, last one. So on this one, it's a little bit different. This goes on forever, and this goes on forever. These ones are the odds, and these ones are the evens. And it goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Those are a very special set of numbers. That is known as N, the natural numbers, the counting numbers. So just to summarize what we've done today, I have these things called sets. So let A and B be sets that live within some U, some universal set that holds all of them. I have a complement, which means if I have some set A and then I write A prime or A complement, I'm looking for the things that are not in A. I can intersect two sets. What do they have in common? Or I can union two sets. What happens when I put all of both sets together? And those are the major things you need to know about sets.